The system that we're going to model is similar to a serial production line. So customers enter the restaurant and then they go to the first stage where they choose the type of bread and meat and cheese that they want on their sandwich. And then the customers go to the next stage, which is the oven. So if they want their sandwich toasted, uh, the worker puts the sandwich in the oven, and the oven uh, heats the sandwich and toasts it. And then the customers will go to the third stage, which is the veggies station, where they put lettuce, tomatoes, and other types of vegetables and condiments on their sandwich. Once the sandwich is ready, the customers pay at the cash register, and um, after the payment is complete, the cashier puts the sandwich in a bag, and the customers then go to the drink machine and get their drink, and then they leave the system. The data that we're given are as follows. So the arrival rate is 32 customers per hour. The service times are all triangularly distributed for all of our 5 stages in our system. And the parameters of our triangular distributions are as follows. So for example, for the bread and meat station, the minimum is 1 minute, the maximum is 2 minutes, and the most likely value is 1.5 minutes. Similarly, for the oven, the minimum mode and maximum values are half a minute, 1 minute, and 1.5 minutes. The other thing is that not all of our customers want their sandwich toasted. So the data that we're given indicates that only 70% of the customers want their sandwich toasted and 30% get cold sandwiches. However, the current operating policy of this restaurant requires that we maintain first in, first out throughout the system. In other words, we do not allow customers who want cold sandwiches past the customers that are waiting for their sandwich to be toasted. As for the performance measures that we're interested in, um, particularly we want to evaluate server utilizations and also average time in system and expected number in system um, at steady state. So now we can jump to Simio and start building our initial model. So the first thing I need is a source object. And let me zoom out here a little bit so it can fit my model here. I need 5 server objects. And I can either drag and drop my server objects one by one on my facility view, or I can simply double click on the server object definition in the standard library, and then I basically switch to multi-place mode. So now I can place multiple server objects on my facility view without having to go back to the standard library and actually um, uh, drag and drop another server object every time I need one. So in order to exit the multi-place mode, you can either hit escape or simply right click. So the next object I need is a sync object to destroy the entities that exit the system. And I also need my default entity object instance. So the next step is to connect my servers together. So I'm going to, again, double click on my connector object definition. So now I can simply connect all my objects together without having to go back to the standard library and select connector every time I would like to add a connector to my model. So now that I have my initial model set up, I can hit run and basically watch the model run and make sure that everything is connected and everything is working correctly. The next thing I would like to do is rename the objects in my model. So I'm going to start with my model entity and I'm going to call it customer. And I would also like to rename the other objects, so I'm going to rename my source to enter. This is my bread and meat. And then I have my basically oven. The third stage is the veggies. Fourth stage, cashier. Fifth stage is the drink machine. I'm going to call it drink. And finally, customers exit the system. Now the next step is to input the parameters of our model. So um, I'm going to go back to my PowerPoint for the parameters. So I know the arrival rate of customers is 32 customers per hour, which is Poisson. So I know that I'm going to have exponentially distributed inter-arrival times. So when I click on my source object, I can see its properties on the right hand side in the properties window here. And as you can see, the default value is exponentially distributed with 0.25 minutes as the average inter-arrival time. And I know that my customers arrive at a rate of 32 per hour. So I can simply change that to inter-arrival time by changing this value to 1 over 32, which will have a unit of in hours. So I'm going to change my units to hours. So now I have my inter-arrival time exponentially distributed with mean 1 over 32, and the units are in hours. So the other parameters are servers service times. So back to my PowerPoint. So for the bread and meat, we have 1.5, and 2 minutes for the parameters of my triangular distribution. So I can simply go ahead and change these values to 1, 1.5, and 2 minutes. And I know I'm going to have the exact same processing time distribution for the veggie station. So I'm simply going to copy this expression and paste it for my veggies station. For the oven station, we know the parameters are 0.5, 1, and 1.5. So I'm simply going to change this to 0.5, 1, and 1.5. And I'll make sure that the units are in minutes. And I know my cashier and my drink machine also has, or both of them have the same processing time distribution. Now remember, there is still one more thing that I haven't incorporated into the model, and that is the fact that for the oven station, I'm going to have different processing times for my customers. In other words, remember that based on the current operating policy of the restaurant, we need to maintain first in, first out throughout the system. So basically, we route all of the customers to the oven station. However, we know that for those people that will get cold sandwiches, the processing time on the oven station is going to be 0. So I need a mechanism here to have different processing times based on the percentages that I'm given in the problem statement. So basically, I want a 0 processing time for 30% of my customers that get cold sandwiches, and for the remaining 70% of the customers, I want this expression to be the processing time. So in order to do that, I'm going to go to Simio Expression Builder, and I'm going to type random and then hit period to get to the submenu. And in the submenu, you will see that we have a list of different probability distributions that we can use. And in fact, one of these probability distributions is a discrete probability distribution. And if you hover the mouse on it, you can read the description that says the discrete distribution is an empirical distribution defined by a set of value and cumulative probability pairs that define a stepwise linear cumulative distribution function for a discrete random variable. And this is exactly what I need. So I'm going to double click on the discrete probability distribution. So the first thing that I need to put is the first value, which is 0 processing time. And I know that I want this to be for 30% of my customers. So the second variable here will be, the second parameter will be 0.3. And for the remaining 70%, I want it to be random, triangular, with parameters half a minute, 1 minute, and 1.5 minutes. And I know that the rest of my customers will have this value associated with them, so I'm just going to put 1. So this way I can guarantee that for 30% of my customers randomly, I will have a processing time of 0, and for the remaining 70%, I will have this triangular distribution for the processing time. So now in order to verify that this is working, I can run my model and look at the model and how it runs. So for some of the customers, I expect them to skip the oven station in 0 processing time and go to the veggies and cashier and drink. But since this is hard to capture by just looking at the model run, an alternative way to make sure that this is actually working is to use the step function or the step mode as you run the model. So every time you hit the step button right here, the model jumps to the next event that is going to be processed in your simulation model. So I keep clicking on step until my entity arrives at or enters the processing station of the oven station, and I will then look at the current time, and what I would like to see is that for roughly 30% of the customers, I want them to exit the processing station of the oven station in 0 simulation time. So let's see what happens to the first entity. So the current time is 12 0133. So I'm going to hit step, and as you can see, the simulation time is changing or evolving. That means basically this entity had some processing time associated with it, which was non-zero. So I'm going to continue running my model till my second entity arrives, and my second entity will now go to the oven station if I continue running my model, and this is right here. So now the current time is 12:04:23, and I continue clicking on step button, and as you can see, in 0 simulation time, my second entity exited the processing station of the oven. So I'm still at 12:04:23. So I can continue this process and verify that my discrete probability distribution that I have used for my processing time on the oven is working. But based on what we just saw for the first entity, it looks like that we sampled from the triangular distribution, while for the second entity we had a 0 processing time. So I want you to continue running your model in the step mode for several other entities and verify that your processing time is actually working correctly. So in order to further verify my model, I would like to compare it to an analytical model that I have developed. So here is my static queuing network analysis, and where I have estimated um, utilizations of my servers and number in system and time in system at steady state. So what I would like to do is run my model and compare these values together. So I'm going to um, increase the run length to 100 hours, and I'm going to run my model in the fast forward mode and then go to my results. And when I look at my number in system and time in system, I'm getting 5.17, and let me change the units to minutes here. So 5.17 for number in system, and average time in system 9.44. And when I compare these values to my static model, you will see that the values I get from my simulation model are much lower than my expected values. This difference is due to a couple of reasons. First of all, in my queuing model, I'm assuming that all processing times are exponentially distributed, which is not the case in my simulation model. Secondly, my queuing model assumes that everybody has the same processing time in the oven station. So basically, my queuing model ignores cold customers. And finally, we know that from our simulation interactive run, we're only getting one observation of these random variables that we're trying to measure. So in order to get a better estimate, we need to replicate our model to get multiple observations. So now I'm going to make these changes, or basically modify my simulation model in order to make it correspond to my analytical model. And before I do it, I would like to save this model, and I would like to call it current policy. And now I'm going to change all my processing time distributions to exponential, and also I'm going to remove the discrete empirical processing time I have for my oven station, so everybody will have the same exponential distribution in my verification model for the oven station as well. So here is my modified model for my verification analysis. As you can see, I have changed all my processing times to exponential distribution with the same means. And of course, for the oven station, I have also removed the empirical distribution that I had. So now everybody is treated exactly the same on the oven station, similar to my analytical static model. So now, in order to replicate our model, I'm going to project home and create a new experiment. And I'm simply going to run my model for 10 replications and look at the results. So now the run is complete. I can go to my pivot grid and compare my values. So let me filter out the values that I don't need real quick. So I need the average in minutes, and percent values. And of course, the only data items that I need are number in system, scheduled utilization, and time in system. So now I have filtered my pivot grid to down to the performance measures that I'm interested in. So now I can go ahead and compare my values with my analytical model. So as you can see from my number in system, I'm getting 11.11, while I expect to see 11.4, 42. And for the time in system, I'm getting 21.06, while I'm expecting to see a little higher value of 21.42. So as you can see, it seems that our values from the simulation models, although our scheduled utilizations seem to be close to our expectations, but our time in system and number in system seem to be lower than what we expect them to be. And that's mainly due to the fact that when we start our model, we have an empty system. So we start with 0 number in system, while at steady state, we expect to see 11.42 entities in the system. And also, for the first few entities, since we start with an empty system, we don't really expect them to wait in any lines in order to get processed. So for these entities, we expect their time in system to be much lower than what we typically see in at steady state. So in order to solve this issue, without getting into the theoretical and technical details, what we need is something we call warm-up period. So what I'm going to do is run my model for 300 hours, and I'm going to add 100 hours of warm-up period. So what the warm-up period does, it um, removes or deletes the statistics that we collect during the first 100 hours of simulation run. So we hope that this would help us remove some of this initial bias that we have in our results. So now when I look at my, let me reset and run my model, run my experiment again. So now I can go to my pivot grid and compare my values, and now as you can see, I'm getting 11.8 instead of 11.4, and I'm getting 21.9 instead of 21.42. But when I look at the half-width, it seems that all my expected values fall within my confidence intervals. So now I have collected some evidence that my model is implemented correctly. And of course, if I would like to verify my model even more, I could either increase my number of replications to get more observations of my random variables. Alternatively, I could also increase my run length to hopefully get closer to steady state. And I could also increase my warm-up period to reduce the impact of the initial transient bias on my simulation outputs.